So that's uploaded, so you guys can watch that. Let's have a quiz, and then we'll move on to chapter 11.2 because I've already uploaded 11.1. Let's invent a quiz real quick.
When is the test for chapter
10? Great question. So chapter 10 was kind of short, right?
Mm-hmm.
And that's going to get included with all of chapter 11. So chapter 11 has, I believe, 8 sections. Let's go. Yeah. I believe the last section is 11.8 Lagrange multipliers. So I want to include 11.8. So there's 8 sections in chapter 11, 3 sections in chapter 10. So those will all be dumped into the second exam. Yeah. I really want to get the Lagrange multipliers in there. So let's see here. Okay, so number 1, given r of t is a position function, cosine of t, sine of t, cosine of t, sine t. Find the velocity vector, find the acceleration vector. So here's A, B, and let's include a C here, A, B, and C. Find A of pi, V of pi over 2, and R of pi over 4. Now let's just leave it at that. No number 2, because I want to move on to 11.2. This is a big section. You guys have 11.1 recorded and on Zoom, so you guys can watch that lecture. See who's watching here virtually. Oh, there's no one virtually. That's sad. It's always not nice chatting with you guys virtually. Welcome, Caleb. Please email me your solutions to the quiz problem. It's just a one problem as a part A, B, and C. Got about a minute left. All right, pass those in and come get them actually. Thank you. Thank you. Okay, let's move on to 11.2. This is where it starts to get good. Limits and continuity. Okay, so let's say we have some function of two variables, f of x, y. Let's say we define it to be like sine of x squared plus y squared all over x squared plus y squared. And let's say we have some g of x, y, a different function defined like the difference of x squared and y squared, and the sum of x squared and y squared. Okay? Just like how we could calculate the limit, like as x approaches a of f of x, so too we can calculate the limit as a pair of values approaches a pair of evaluated values. So let's say my f, let me invent another one. Let me invent an h of xy. Let's say it equals x plus y, just to keep it simple. Well, I can calculate the limit as x, y approaches, like 1, 2. And then of this function. And that would just equal 1 plus 2, which is 3. So it's just like our ordinary one-dimensional limits, except now it's two-dimensional. We wish to analyze what is the limit as x and y approach 0, 0 of f of x, y. And you'll see that doing limits in this case get more complicated. Okay, they get more complicated. Whenever you compute, like the left-handed limit, approach 0 from the left and 0 from the right for both of these. And whenever you do it from the right and from the left, you can check in your book. They have a table, table 1 and table 2 of 11.2. So for f of x, you notice that it approaches 1, whether you're approaching it from the left or the right. So this thing will approach 1 whenever you just check this guy right here. Whenever you plug numbers and check, that's really the only way we can do limits. Limits don't equal 0. Notice if I do direct substitution, I get 0 over 0, which is undefined. But that's what a limit is. It says I'm not going to actually put in 0 for x and y. I'm going to infinitely get close to that value, but not really be that value. What is the result of that? Well, the result of that ends up equaling 1, whether you approach it from the left or whether you approach it from the right. But this guy, if you approach it from the left, notice it becomes like -1. And when you approach it from the right, it becomes +1. So like the left hand and the right hand limits don't agree. So this limit does not exist. So we'll be doing a lot of that in this section. We'll be doing a lot of that in this section, and it's actually really fun. It's actually really astonishing. So we realize that the limit of some x, y approaching some a, b of some f of x, y, only if it equals f of a, b, is it what we say it's continuous. This is continuous. A, B, and it does not matter what path we choose. In 2 dimensions, we only had 2 paths: approach it from the left or approach it from the right. Well, now we're in 3 dimensions, and these functions are creating surfaces. So we can approach it almost with an infinite amount of different paths, because there's like an infinite amount of different like orientations that you can like approach a certain value. So here's what I mean. In 2 dimensions, here's some a. So the limit as here's my f of x. The limit as x approaches a from here, and the limit as x approaches a from the left and from the right, they converge to give us, our f of a. So the limit exists and it equals f of a. But in 3 dimensions, let's say you have a surface, and here's your point, f of here's a function f of y, and this is at the point evaluating f of a, b. Notice that if the you can like approach a surface like this, and you might get one answer, but you might approach a surface like that and get a different answer. How can I explain this? Okay, so like think about going up a mountain, or like going hiking, okay? You're going up the mountain on the hiking trail, so you can like kind of go up because it's nice and smooth. But what if you like leave the hiking trail and try to go up those weird undulations? You experience that the curves and the surface are different there, even though it's on the same surface. It's because you're approaching your destination by a different path. So this is saying that your limits have to actually be the same no matter what path you approach this point on the surface. So let's see an example of this. Let's see an example of this at play. Let's evaluate the limit as x and y approaches 0, 0 of this function. Okay. Direct substitution only gives me 0 minus 0 squared over 0 squared plus 0 squared, which I just get 0 over 0, undefined. Don't even think about using L'Hopital's rule or anything yet, because it's a function of 2 variables, right? You'd have to go to implicit differentiation, and let's not go there. because you won't get what you want even if you try. So then, okay, we think, well, I'm approaching 0, 0 in a very direct way. Why don't I approach it along the x-axis? Because this surface is, I mean, it actually exists everywhere because the domain, the only time something could go wrong is if you divide by 0. So the domain of this function is equal to the set of all x, y, and element of R2 such that x not equal, oh, well, actually mutually, x and y do not equal 0. Because if they mutually equal 0, then their sum will add up to 0. Furthermore, another thing you can say is that x squared plus y squared, that doesn't equal 0. This is in the case in which they're both equal to 0. But their squares might end up, you know, well, even if there's a negative number, actually, if you square it, that takes away the negative values. So the only way to get two squares to add up to 0, right? Because even if we input negative numbers, it'll make them positive. So the only way to get two squares to add up to 0 is if they were 0 themselves. Because a negative number would then become positive, which would then become non-zero, the sum. So let's approach this along the x-axis. Notice along the x-axis means that the y variable is set equal to 0. Just like in 2 dimensions, the x-axis, any point here can be represented as some x comma 0 for variable x. So the same thing is true when you add the third dimension, z. So let's take the limits as x, y approaches our point of interest 0, 0, but along the x-axis, meaning x is 0, y is 0 and x is arbitrary, some arbitrary value of my x squared minus y squared, or x squared plus y squared. Notice that now I substitute in for y 0 and in for x, x. So notice that the numerator and denominator cancel to give me 1. So the limit just must be 1, right? In these multivariable functions, it's not as simple as just calculating one limit and seeing that it equals 1. It has to equal 1 for any path taken, for any and all paths taken. Okay? So let's check whether another path changes things. What if I go along the y-axis? Well, now I'm taking the limit as xy approaches along the y-axis, x is set equal to 0 and y is arbitrary of this function. Oh, but what that does is it makes this. And this becomes negative 1. Uh-oh, the limits don't agree. Based off of the path that I took, the answer is different. The way I like to think about it is like, I can climb a hike trail, but if I leave the hike trail and actually try and get to that same spot, if there's like a huge boulder and I can't climb it, then I can't get to that spot. So the limit really exists if it doesn't matter. So let's say you're on some like plateau or some mesa on the hike. Then actually the limits would all agree because it's a flat section on top of the mountain. Then all the limits, all the paths, if I tried to get to one point, would agree because it's all flat. But if it's like curvy this way and then straight this way and then a dip this way, a depression that way, the limits will not agree. And your book does a good job of showing you a bunch of surfaces generated by the computer algebra system Maple. Okay, so notice that we found that the limits don't agree. This limit does not exist. Because it shouldn't matter what path we take. D and E does not exist. Yeah, these limits get more complicated than the limits we did in Calc 1. Because of this fact. So let's check whether the limit of xy approaches 0, 0 of x times y over x squared plus y squared exists. Okay, let's just try direct substitution again. I get 0 or 0. Okay, let's try approaching it along the x-axis. Okay, that means my y is set equal to 0, and my x is just x. Okay. Let's approach it along the y-axis. Okay, again, the numerator becomes this becomes 0 times y over 0 squared plus y squared. And this is 0 over y squared, 0. Oh! Voila! They agree. The limit exists. Or does it? We only check 2 paths. There's technically an infinite amount of paths to check. Right? Notice that, well, what if I approach it along the line, the simple line y equals x? Well, then I get the limit. Xy approaches y is equal to x. So it's that. Okay. Of our function, xy all over x squared plus y squared. Okay, so then this becomes x squared, technically, plus x squared plus x squared. Right? Well, then that's x squared over 2x squared. Cancel, cancel. What in the baby Jesus is happening? Now it doesn't equal 0 like when you approach it along the x-axis, and as you approach it along the y-axis. Now it's equaling 1/2. So yeah, we celebrated too soon. It should equal a consistent value no matter how we approach it. It should, but it hasn't. So the limit does not exist. So we could have tried another line. In my preparation for this class, I tried this line, but things didn't cancel out easily to get like a beautiful number like 1/2. So if you're just sitting there trying to solve problems like this without the answer right away, try things out. And then you'll see that, okay, I can try things out, but then there's also like a good educated guess. Because when you just make it x equal to y, you realize this becomes x squared. These become 2x squared, and there's some beautiful canceling that will occur. So the lines in which you pick to approach these functions, pick them wisely. Pick them wisely so that things cancel. Well, let's try a different one. What about the limit y approaching 0, 0 of xy squared over x squared plus y to the 4th? This is a different guy. Direct substitution gives me 0 over 0. That doesn't work. the direct substitution days. I mean, even in Calc 1, direct substitution almost never worked. You had to do some work to make it work. So let's approach it along the x-axis. Okay, so then that's the limit as x, y approaches x comma 0 on this thing. Okay, so I replace all my x's with the x and all my y's with the 0. Oh, that's a 0. Wow. How about I approach it along the y-axis? Let's see what happens here. So I get the limit as xy approaches 0y of my xy squared, x squared plus y to the 4th. Okay. This becomes 0 at the top. And the bottom just becomes a y to the 4th. Oh, that's 0. But we know from our previous experience that this is not time to celebrate yet. Okay. What about that other technique? What about along y equals x? Okay, the limit of xy approaches x and, x of xy over, xy squared over x squared plus y to the 4th. Okay, so then this becomes x times x squared over x squared plus x to the 4th, x cubed over x squared plus x to the 4th. So what if I factor out x squared out of the denominator? It becomes this. This is this. I can cancel these out. I get x over 1 plus x squared. Okay, so what if I take the limit of that? Whoop. This is an x. This is a 1 for x squared. Oh, and then I get this. Zero. Hey, it equals 0. So what's going on? They're all agreeing, right? So the limit must be that. No. You could actually even plugged in y equals mx. Let's approach it along the line y equals mx, even more generally. X and y equals mx of x, y squared over x squared plus y to the 4th. This ends up equaling x times mx squared over x squared plus mx to the 4th. This is x squared over x squared plus m to the 4th, x to the 4th. This is x cubed m all over x squared factored out. I get 1 plus m to the 4th x squared. Cancel.
Professor,
Yes.
the m should be squared.
Wait a second. Oh, thank you. I did drop the squared. Thank you. Okay, and then cancel here. So I get m squared x all over 1 plus m to the 4th, x to the 4th. Oh, squared. There we go. Okay. So I take the limit of this guy. We're getting what we had earlier, That's true in general. So that means the limit is equal to 0. Sammy's like, you keep lying to us. So I'm not going to believe you now either. So let's check out. So yeah, I am lying. You guys don't get how fun it is to troll students. One, actually, it's a good way to like test their understanding. But two, it makes them realize I just can't like blindly write in my notes everything he's saying, because like maybe like 5 seconds later, maybe like a minute later, he'll be like, oh no, that's not right. So okay, what about along a parabola? This is so cool, guys. We're doing really cool math. Like, we approach it along the x-axis. We approach it along the y-axis. We approach it along y equals x. We approach it along the arbitrary line y equals mx, with no with the y-intercept being the origin. They all equal 0. But what if we like approach this curve using a parabola? And you know that parabola y equals x squared intercepts our region of interest 0, 0, right? It sits on it. So let's approach it along this. I know what you're thinking. I mean, are we gonna really have to like do an infinite amount of work just to prove a limit exists? You guys will see that no, that's why theorems kick in. That's why mathematicians are really powerful when they make theorems. Overarching theorems allow us to not have to do an infinite amount of things, which is really, really cool. Even your computers won't be able to do an infinite amount of things, right? They can't. Not even a quantum computer, even though it's going to be faster than what we have now. Okay. My x needs to remain an x. And my y needs to change to an x squared. That's right. The x needs to remain an x. Okay, and then the y is substituted with an x squared. So notice what we get here. I get x times x to the 4th over here. X squared plus, yeah, x to the 8th. So this becomes x to the 5th over x squared plus x to the 8th. So we cancel some stuff out here with my factor. I get okay, so I cancel, I get x cubed over 1 plus x to the 6th. Again, when we do that limit business, this equals 0 over 1, which is 0. What if we flip the parabola? Remember y equals x squared is like a parabola like this, but x is equal to y squared would be like a parabola like that. It's okay if you don't remember. You're straight. So remember, y equals x squared in 2D gives me a parabola like this. But x is equal to y squared. What does that look like? All you have to do is take the square root of both sides to see. You get y is equal to plus or minus root x. And square root of x is like this. So the plus or minus part, the minus part gives you this. So that's why y equals x squared is like this. And then y equals, x equals y squared is like this. Looks like a kamehameha. You guys seen Dragon Ball Z?
A little bit.
You know what Dragon Ball Z is? Yeah. It's like a cartoon show where they shoot energy beams out of their hands. It's kind of cool. All right. So let's consider this path. It still intercepts our region of interest. What about x is equal to y squared? Limit xy approaches y squared y. X, y. Oh, I keep wanting to make that the exponent. There we go. Surely this won't change things. X is y squared. Y is just itself. X is y squared. Y is just itself. This is y to the fourth. Nope, this is y. Yeah, the whole thing becomes y to the fourth. This becomes y to the fourth plus, y to the fourth. This is why it's so beautiful. Because it's just like last time. Now we're going to get y to the fourth over 2y to the fourth. Now the variables can cancel, so it's just 1/2. It was supposed to equal 0. But it doesn't. Notice how just this pathway thought it was 0, but this pathway did not think it was 0. This pathway is taking the hiking trail. This pathway is deciding I'm going to not take the hiking trail. So what do we do, man? Like, are we going to just sit here and evaluate limits for the rest of our lives and still not be able to prove it? You guys remember the squeeze theorem? This thing is really cool. Or as you young kids say, it's really tight. I would say that growing up too, so I guess I'm young. You guys probably say different things these days. Okay. It says that, okay, let's say I have some function f of x. This is the first 2D version. We'll talk about the 3D version. All right. Then let's say I have some function g. And then let's say I have some another function h. Okay. It says that if, clearly f, g, and h are continuous, real valued functions along a bounded interval, if this condition holds, if, let's say, h of x is always less than or equal to f of x, which is always less than or equal to, this should say g of x because it's the one in the middle, and this should say f of x because it's the one on top. So if this holds, and the limit as x approaches some a of h of x is equal to L, which is equal to the limit as x approaches a of my f of x. So the limit for the top function is L at some endpoint a. Here's my L right here. And the limit of f of x as x approaches a is L. And this function is below, and this function is above g of x. The squeeze theorem says, okay, we may assert the squeeze theorem says, given these conditions that hold, that implies that the limit as x approaches a of my middle function g of x is the same as the limits of the functions that bound it by above and by below. That coupled with this information, the limit as x, y approaches AB of x is clearly a by direct substitution, and the limit as xy approaches a, b of y is b by direct substitution, and that the limit as xy approaches a, b of some constant c is just a c, because there's no x or y to change it. Assuming these limit laws in 2 dimensions, the squeeze theorem holds. So let's try our hand at actually proving something. Because you can do a 3-dimensional or 2-dimensional squeeze theorem. Just these functions aren't just a variable of x. They're x, y. So for example, no! You didn't even have to tell me class was over. I'm realizing class is over. I'm not even through the section. This is really annoying. On quiz days, I don't get to really get through a section. So I'll assign the homework, but I won't make it due exactly a week from today. And maybe like not following Friday, but the Monday afterwards or something like that. You guys know I'm flexible and reasonable. If you need more time, tell me, and I'll give you some more time. Yeah, to do your homework, especially if you're trying to like turn in really good work. That makes me so happy that you guys are like putting in that kind of effort. That makes me really happy. So leave this here. I'll leave this here. Yeah, we didn't get through all of it. I was just about to get to the good part, where we can actually prove the limits exist using the squeeze theorem. That's like one of the only ways I know that it can be proven. Because the theorem gives you the limit, and then you don't have to check for an infinite amount of cases. Yes, ma'am.
Can I ask you a question about my pen?
Oh, yeah, sure.